So you may or may not have noticed that this semester is called AP Physics C, Electricity and Magnetism, and we haven't done any magnetism yet. Well, today we start. So we are first going to talk about the effects of magnetism, the force that magnetic fields exert on objects. We will talk in a couple of days about where these magnetic fields come from in the first place, but right now we're going to see the observed effects. So I'm going to write down two equations. F equals QV cross B, and F equals IL cross B. Oops, put that over the wrong thing. L has the vector. Okay, so there are a couple of things I want to say about this. First of all, notice that this force says we've got a charge and it's got some velocity. Magnetic fields only exert forces on moving charged objects. Only. If it's not charged, there's no magnetic force. If it's not moving, even if it is charged, there's no magnetic force. B is the symbol for magnetic field. No one knows why. Just like I is the symbol for current, no one knows why. B is the symbol for magnetic field. So this equation, by the way, forgot to write that there, this says there's also a force on current that has some length in a magnetic field, because current is moving charges. So you know Q is charge, V is velocity, B is magnetic field, I just told you that. I is current, L is the length of the object in the field, and the length of the wire in the field, and then B is magnetic field. So let's talk units. If we rearrange this equation, just write it as a magnitude, B equals F over QV. So the unit of magnetic field must be a Newton divided by a Coulomb times a meter per second. This is called a Tesla. The symbol for the Tesla is a capital T. It is really interesting now that we have a car company, Tesla, which is electric vehicles, but it's actually the unit of magnetic field. Now, the car company is actually named after Nikola Tesla, which this unit is also named after, and they both evolve electromagnetism, so it works out. You can see the unit also works out for the other version of the equation. B is F over IL. So we again have a Newton. Current is in amps, and then length is in meters. Well, an amp is a Coulomb per second. So Coulomb per second times a meter, well, you just move the per second to the other side, so it is the same thing. Having a magnetic field that's in the Tesla range is actually fairly difficult to do. Most magnetic fields that you've encountered in your life, unless you've had an MRI, were on the millitesla or the microtesla range. The Earth's magnetic field is it's in, depending on the location on the Earth, around the 10s or 20s of micros. So not a real strong field. But now let's go back to some of the other features of this. So calculating magnetic force is pretty easy. F equals QVB. But then we have this X in here. And when I read this equation, magnetic force equals charge times velocity cross B. This is, if we multiply two vectors, we need the cross product. We had this before. Torque is R cross F. And you know then that that was RF sine theta. So we get the same thing here. So the magnitude of the magnetic force is QVB sine theta, if it's a moving charge particle, or it's ILB sine theta if it is a current carrying wire of some length. The angle is between V and B, or L and B. So we know we're going to get the most force if this is the maximum and the sine function is maximum at 90 degrees. So you get the most magnetic force when a charged particle is moving perpendicular to the magnetic field. If it's moving parallel to the field, then V and B are in the same direction. This angle would be 0, and there's no magnetic force. Same thing with a current carrying wire. If you want the most magnetic force, you put the current across the magnetic field. If you want zero force, you put it with. If it's in between, you just do the sine theta. But now let's talk about directions. This kind of came up with torque, but we didn't really do it with torque. But magnetic force is three-dimensional. The force is a vector, it has a direction. And we've got this weird, we multiply these things. And so it turns out, from observed, this is not something we made up for the fun of it, from observed quantities, that whatever the directions of the initial velocity in the magnetic field, the resulting force is perpendicular to the two of those, whatever plane they define. So we need to be able to work three-dimensionally. On this paper, I can draw arrows. So this arrow means to the right. This arrow means to the left. This arrow means towards the top of the page. This arrow is towards the bottom of the page, and I'm using those really carefully. I'm never going to use the words up and down, because here's the problem. I need a third direction. I can have this direction, right and left. I can have this direction, top and bottom, or I can have this direction coming straight out of the paper. So I have to have two more symbols. A dot is going to stand for out, and an X stands for in. The way you remember this is still an arrow. So there is an archery arrow under the desk. Someone down there, miniature, is firing it up at us. So right as that arrow, the arrow, comes through the paper, what I see first is the tip of the arrow, a little tiny dot coming up out of the page. Oh, I just said the word up, and I'm never going to say up. The X is if I have an arrow up here and I'm firing down into the paper. So the back of the arrow, if you've ever shot archery, has little feathers to stabilize the flight on the back, and there are really 3 of them, but it's faster to draw an X. So this is the last view of that arrow we fired down into the paper. Right as it finishes passing through the paper, we see the feathers on the back. So the reason I'm not going to say up and down is because sometimes we have used the top of the paper to mean up and the bottom of the page to mean down. Other times we mean vertically, so in this classroom, up away from my desk to be up and down towards the floor to be down. So up and down don't work because they mean 2 different things depending on the context. So top of the page and bottom of the page, I can draw arrows. Out of the paper, away from the desk, or into the paper, towards the desk, are going to be our useful words. Now sometimes you're going to have drawings with arrows. Other times you're going to use the coordinate system. You know that on a coordinate plane, this is positive x and this is positive y. So to the right is positive x, to the left is negative x. Top is positive y, bottom is negative y. So then we just need to deal with out and in. We have the third axis, the z-axis. Out of the page is defined to be the positive z, and into is negative z. It's the definition. Just like we didn't have to make this positive x, we could have chosen to make this positive x. We could have made this positive y. We didn't choose to. We chose positive x and positive y, and so the third choice is out of the page is positive z. And now that we've defined our direction symbols and talked about the z-axis, we can go back to this equation. So if I rewrite it, the magnetic force is equal to QV cross B. We are going to use what is called the right-hand rule. In the right-hand rule, you are going to hold your hand in this position. You're going to turn it lots of different ways, but you're always going to hold it like this. You can turn it, you can do all sorts of things here. But you're going to lock it in this position. And then your fingers, different parts of your hand have different assignment. Your thumb can point, like it's like an arrow. Your thumb is the direction of the velocity. Your fingers are the direction of the magnetic field. And your palm shows the direction of the force. So if I have my hand like this, my thumb is pointing to the left, my fingers are pointing towards the top of the page. So this is V, this is B. My palm is facing into the paper. So if this was a moving charged particle to the right, excuse me, that's left, to the left, and the magnetic field is towards the top of the page, the force the particle would feel is into the page, x or negative z. And I'm going to draw this to show you some of the lining up. So first example, we are going to have a magnetic field towards the top of the page, blue for magnetic field. And then I'm going to have a positively charged particle moving to the right. So the question is, what's the direction of the force? I always line up my thumb first. So let me make sure this is really clearly on the screen. So if I just put my hand on the paper, I've got a problem. V is pointing the wrong direction. My thumb needs to point to the right. So I'm going to turn my hand over. Now, just by turning my hand over, I'm now matched. My thumb points to the right, kind of off the screen. My thumb points to the right. My fingers point towards the top of the page. And so my palm is facing, if it was about to slap somebody, away from the paper, out of the paper, the dot symbol. So the force here is out, or the dot. Okay, so let me do that again. You can do it in any order, but I personally always do my thumb first. So my thumb, I turn, like, let's just say I put my hand down like this. Got it locked in position. I need to turn, so my velocity is over this way. But then I need the magnetic field, my fingers, to point towards the top of the page. So I go this way. Now they match. The velocity, red arrow, is my thumb. Magnetic field towards the top of the page. The palm is away from the paper. You are allowed to label your fingers. So if you want to get a friend, because most of you would need a friend to do this, to label V on your thumb, B on your fingers, and F on your palm, you are allowed to do that, and you can do that the day of the test. The reason I say you've got to get a friend to do it for you is because this is the right hand rule, and most of you are right-handed. If you use your left hand, you get the wrong answer. Let me show you that. I need my thumb to point to the right. If I use my left hand, thumb to the right, fingers towards the top of the page, but my palm is pointing into the paper. But the correct answer is out of the paper. We already figured out. So left-handed people, you are at an advantage here, because when you need to do one of these problems, you're just going to say, oh, okay, I've been writing on my paper, move my hand, here's the direction. Right-handed people, you will have to, working on the problem, put down your pencil, use your right hand, figure out the answer, pick your pen back up, and answer the question. Do not use your left hand. You have to use your right hand, or you will get the wrong answer. So we're going to do a couple more examples. If we have a magnetic field that points into the page, remember X means in because that's the back of the archery arrow. So B is in. And I'm going to make the positively charged particle move towards the top of the paper. So I just put my hand down. It's totally wrong. I need to turn my thumb so it matches the direction of V. So turn my hand so it points towards the top of the paper. And then I need my fingers for the magnetic field to point into the paper. So I need to turn my hand vertical, kind of hard to see with this camera, vertical, so now my fingers are stabbing into the paper, just like these X's are the back of those arrows. So velocity towards the top of the screen, my fingers going into the paper, and my palm points to the left. If I move my hand this way, my palm pushes to the left. So the force is to the left. Okay. Next example. I'm going to have a magnetic field towards the bottom of the page. And now I'm going to have a current carrying wire to the right. We didn't talk about current carrying wire, but if we go back to our definitions, our two equations are almost the same. So F stays the same, B stays the same. QV is replaced by I and L. So whatever the direction of the current, you use your thumb to do that. So your thumb is both the velocity and the current direction. So I flip back to the third example. So I put my hand on the paper. My thumb, which is I or V, points directly to the right. but I need my magnetic field to point towards the bottom of the page, so I have to turn my hand over. And you can see my palm pushes into the paper. So the force is X into. Don't hurt yourself. This is very awkward to do. You are welcome to turn your paper. If I turn my page around, oops, I hit the camera. If I turn my page around, I can match this one right there. I to the left on the paper, B to the bottom of the paper, but I see my forces into the paper. So my answer is into, even though it's upside down. I could do that on this question too. If, make sure it's on the screen, my thumb needs to point towards me, magnetic field into the paper. So my palm points that way across the paper. I don't want to think about right and left because I know I personally would get confused with having to turn my paper around. So what I would do in this situation is I would draw F is that way. And then when I turn my paper around to actually write my answer, I'd say, okay, now in the correct orientation, F is to the left, F is to the left. Okay, so they always match. Now, I gave you one twist on the right-hand rule by telling you that the current will also be the thumb, just like the velocity. Well, here's a second thing. I made a big deal about making this was a positive particle, and you know current is defined as the direction of motion of positive particles. Well, what about a negative particle? So we are going to do another question, because I'm also going to change what the question is. We have a velocity of a negative particle, negative q. It has a velocity in the positive z direction. So positive z, remember, is out of the page. That's the dot symbol. So this velocity is out of the page. It's a negative charge. It experiences a force in the positive x direction, to the right. This is the force. So now the question is, what's the field? So we have two changes we have to make. One, this time, I've given you the velocity and the force. So when I line up my hand, my velocity needs to point out of the page, a dot out of the page, and I need my palm to point to the right. So I need to turn my hand around, not hurt myself, and now they match. My thumb points towards the sky, my palm points to the right. To make that happen, my magnetic field points towards the bottom of the page. So my answer here, B, is towards the bottom of the page. Now that kind of hurt. So here's what I'm going to do to check myself, except there's one more change we have to make. I'm going to turn the paper to make this a little bit easier. If I point my thumb out of the paper, and now my B, my answer, I've got towards the bottom of the page, I see that my palm does point matching this arrow. I'm not actually going to say the name of the direction because my paper's upside down, but I can see my thumbs match. So this is the right answer, except that it's not, because it's a negatively charged particle. If it's negative, the force is in the opposite direction of the force on a positive particle. You don't need to change anything. You use the same right-hand rule to figure this out, but when you get your answer, you do the opposite. So if I were to test this one now, I need velocity out of the page, I need magnetic field towards the top of the page. That gives me a force to the left across the page. But this is a negative particle, so it would actually experience a force to the right. And so yes, I match my picture. Now, this problem I had originally written on my thing to write differently. That negative q was moving in the positive z direction, and F was in the positive x. Well, I know from figuring this out, B is in the positive y direction. So I have broken this topic into two separate assignments. The first assignment, you're going to calculate magnitudes only. So you're going to use F is equal to QVB sine theta, and F equals ILB sine theta, And it's very straightforward. It should not be a difficult assignment at all. Then, on the second assignment, you're going to do 12 right-hand rule questions. And when you do them, I actually made them multiple choice because your answer choices can only be, remember the list, right and left, top and bottom, in and out, or positive x, positive y, positive z, negative z. So some of the questions I've drawn pictures, and you're going to answer using the words, right and left, top and bottom, in and out. I actually read the words, I didn't draw arrows in the answer choices. Or I'm going to give a question with the directions using the x, y, and z axes, and you'll choose x, y, and z. Now here's one thing that can help you narrow this down. Magnetism has to be three-dimensional, which means on this picture, let's go back to this. I is in the positive x direction. B is in the positive y direction. I have to have the third direction involved. So F has to be either positive or negative z. It has to be in or out of the page. So you use the right-hand rule to figure out which one. But the answer here cannot be positive or negative x because x has already been used. It can't be positive or negative y because y has already been used. It's got to be either in or out or positive or negative z. So, gonna be fine. I'm gonna look for a YouTube video that shows better because me doing this under this camera on the notebook is kind of difficult. So hopefully I'll find one.